Have you ever wondered how colloids are stabilized, making them crucial in numerous fields, including pharmacy? Welcome to the intriguing world of colloids, a tiny universe teeming with diverse particles that are neither truly dissolved nor floating freely. These microscopic particles dance between the boundaries of the states of matter, creating a system that is both complex and fascinating. Colloids are everywhere, from the milk in your morning cereal to the foggy mist that blankets the city. They are key players in various scientific domains, including the pharmaceutical industry. This video will take you on a journey through the protective colloids, the science of colloid stability, the Schulz-Hardy rule, the Hoffmeister series, and their incredible applications in pharmacy. As we embark on this journey, remember, we're not just talking about tiny particles, but about the very essence of life as we know it. Delve into the world of colloids where mystery meets science. Imagine if colloids had bodyguards. Wouldn't that be fascinating? Well, they do, and they're known as protective colloids. In the ever-evolving world of colloids, protective colloids serve as the knights in shining armor. They are large molecules, or a group of molecules that, when added to a colloidal dispersion, prevent the particles from aggregating. They act like a shield, forming a protective layer around the colloidal particles, stabilizing them against flocculation and coagulation. Now you might be wondering, how do they manage to do this? The secret lies in their ability to absorb onto the surface of the colloidal particles, effectively creating a barrier that prevents the particles from coming too close and sticking together. This phenomenon is known as steric stabilization, but their role doesn't end here. Protective colloids also play a crucial part in the formation of lyophilic colloids. These colloids are solvent-loving, and the protective colloid, due to its water-attracting hydrophilic nature, helps in stabilizing these colloids. Their significance is vast and wide-ranging. From the food industry to cosmetics, and even in wastewater treatment, protective colloids contribute significantly. For instance, in the food industry, they prevent the separation of ingredients in products like salad dressings and ice cream. In cosmetics, they ensure the stability of products like lotions and creams. They even play a role in the pharmaceutical industry, where they help in the formulation of drugs and ensure their stability. And yet, despite their crucial role, protective colloids often go unnoticed. They work behind the scenes, ensuring the stability and integrity of colloidal systems. They might be invisible to the naked eye, but their impact is far-reaching, extending to various facets of our daily lives. So next time you enjoy a scoop of your favorite ice cream or apply your favorite lotion, remember the unsung heroes that make it all possible. Yes, we're talking about the protective colloids, the silent shield bearers that work tirelessly to maintain the stability of the colloidal world. So, protective colloids are the unsung heroes of the colloidal world. Ever heard of the DLVO theory? It's not a secret code, but indeed a fundamental concept in understanding colloid stability. Named after its developers, Jaguin, Landau, Verwey and Overbeek, the DLVO theory is a scientific masterpiece that combines electrostatic and van der Waals forces to explain why and how colloids remain stable. So, let's delve into the core of it. Colloidal particles are charged, and this charge creates a repulsive electrostatic force between particles. Imagine two negatively charged particles coming closer. They repel each other, right? This repulsion prevents them from clumping together, thus maintaining the dispersion and stability of the colloid. But the plot thickens. Alongside this repulsion, there is an attractive force at play, the van der Waals force. Now, this force doesn't depend on charge. It's always there, trying to pull particles together. It's like a constant tug of war between the repulsive electrostatic force and the attractive van der Waals force. Here's where the DLVO theory comes into play. It states that the stability of a colloid depends on the balance between these opposing forces. If the repulsion wins, the particles stay dispersed, and the colloid remains stable. But if the attraction overpowers, the particles aggregate, leading to colloid instability. Interestingly, the point where these forces balance out is called the secondary minimum. It's like a sweet spot where particles neither aggregate nor repel each other, holding the colloidal system in a stable state. So, why is this important? Understanding the DLVO theory and the balance of forces helps in predicting and controlling the behavior of colloidal systems. It's vital in many areas, including pharmacy, where it aids in the formulation of stable drug suspensions and emulsions. DLVO theory, a scientific masterpiece that helps us understand the fascinating world of colloids. Ready to decode more colloid mysteries? Let's explore the Schulz-Hardy rule and the Hoffmeister series. Welcome to the fascinating world of the Schulz-Hardy rule and the Hoffmeister series. As intimidating as these terms may sound, they are essentially the keys to understanding the behavior of colloidal systems. Let's start with the Schulz-Hardy rule. This rule is a fundamental principle in colloid chemistry that describes the relationship between electrolytes and coagulation. It states that the coagulating power of an electrolyte is directly proportional to the sixth power of its valency. In simpler terms, the more charged an ion is, the greater its ability to cause coagulation in a colloidal system. This rule provides a theoretical framework for understanding how changes in electrolyte concentration can influence the stability of colloidal systems. Now, let's move on to the Hoffmeister series. The Hoffmeister series, also known as the lyotropic series, is a classification of ions based on their ability to salt out or salt in proteins. In the series, ions are arranged in order of their ability to precipitate or solubilize proteins. For instance, the series shows that anions like citrate and tartrate, which are at the bottom of the series, are excellent at solubilizing proteins, while those at the top, like sulfate and phosphate, are great precipitants. So, what's the significance of these concepts to colloidal systems? Well, both the Schulz-Hardy rule and the Hoffmeister series provide insights into how changes in the ionic environment can affect the stability of colloidal systems. They help us predict and control the behavior of colloids in various applications, including in the field of pharmacy. These two principles are not just abstract theories. They have practical implications in areas like drug formulation, where understanding the behavior of colloidal systems can help in creating more effective and stable pharmaceutical products. As complex as they sound, the Schulz-Hardy rule and Hoffmeister series are vital pieces of the colloid puzzle. So, let's continue to unravel this puzzle in our next segment. Ever thought of the link between colloids and pharmacy? The connection is more profound than you think. In the world of pharmacy, colloids are like the unsung heroes, playing a pivotal role in numerous ways. Their unique properties make them a key component in the development and formulation of various pharmaceutical products. One of the most remarkable uses of colloids in pharmacy is in the creation of emulsions. Emulsions are a type of colloid where two unmixable liquids are combined, often with the help of an emulsifying agent. These are extensively used in the formulation of creams, lotions, and certain types of medications. For example, many cough syrups are essentially emulsions containing oil-based active ingredients dispersed in water. Colloids also play a significant role in the formulation of suspensions, another widely used pharmaceutical dosage form. Suspensions involve the dispersion of fine solid particles in a liquid medium. This allows for the even distribution of the active drug substance, improving its efficacy and patient compliance. Not just emulsions and suspensions, colloids are also instrumental in the creation of aerosols. Medicines for asthma, for instance, are often delivered as aerosols where tiny droplets or particles of the drug are suspended in a gas. But the application of colloids doesn't stop there. They are also used in targeted drug delivery systems. Here, colloidal carriers like liposomes, nanoparticles, and microemulsions are designed to deliver drugs directly to the site of action, thereby improving the therapeutic effect while minimizing side effects. Moreover, colloids have a significant role in diagnostics too. Ever heard of a pregnancy test? The gold particles used in these tests are actually colloidal gold, and their aggregation or dispersion gives the test results. So, you see, the world of pharmacy and colloids are intertwined in ways you might have never imagined. From drug delivery to diagnostics, colloids are involved in almost every step. They're like the invisible strings pulling all the elements of pharmacy together, making the impossible possible. So colloids play a starring role in the world of pharmacy, making them indispensable. As we reach the end of our journey, it's time to summarize what we've learned about the fascinating world of colloids. We've delved into the realm of protective colloids, the unsung heroes that shield and stabilize colloidal systems. We've navigated the scientific labyrinth of the DLVO theory, understanding how it explains the stability of colloidal particles. We've unraveled the complexities of the Schulz-Hardy rule and the Hoffmeister series, peeling back layers of intricacies that govern the behavior of colloids. And last but not least, we've explored the unbreakable bond between colloids and the field of pharmacy, illuminating the vital role these tiny particles play in the development of medicines and drug delivery systems. This, my friends, is just the tip of the iceberg. There's a whole universe of knowledge waiting to be explored. Subscribe for more because you won't find me later. Remember, the world of colloids is as intriguing as it is complex, and there's always more to discover.